Hello. I'm going to start by just explaining that I am an imagery person. I love imagery of planets and stars, and the imagery that's in my presentation has all been downloaded from JPL's Photojournal, which is a website that the Jet Propulsion Laboratory in California has, and you can download lots of beautiful imagery, space imagery from Hubble or Spitzer or Chandra, which are all space telescopes there. And so I've also included some of my wild sort of artistic imagery, which is post-processed, and I've added different algorithms to make it bright colors, or you'll see as we go along. And at the end of the night, we're going to do a meteorite giveaway. So I brought a little iron meteorite. This is an Argentinian meteorite. It's quite common. The crater field covers 3 by 18 kilometers, and there's 26 craters down in Argentina, just north of Buenos Aires. And so it's about 4,000 to 5,000 years old. And underneath your chair, don't check now, but at the end of the night, underneath the chair, one person's chair has a little piece of paper taped under there, so you'll be the winner of the meteorite. Okay, so just going to outline what we're going to talk about. We're going to talk about finding life within our solar system, and the most likely candidates are Europa, which is a moon of Jupiter. So we're going to talk a little bit about Europa, some of the limiting environmental factors on Europa, what are some potential habitats on Europa, and some conclusions, and then talk about what future missions are planned to Europa. Oh, there we go. There's an example of one of my wild artistic images. This is the geyser plume coming off of the southern polar terrain of Enceladus. So Enceladus is a small moon of Saturn, and it has water geysers coming out of its north pole there. And that image has had an edge detection filter, as well as some thresholding. I was trying to bring out the actual water coming off the surface there. Same thing for Enceladus. We're going to look at limiting factors, potential habitats, and draw some conclusions, and then go on to future missions to Enceladus. So this is an artist's rendition of where a former shoreline on Mars was, and I've added some false color to try to give that, the pink is supposed to be where the shoreline is, and just sort of picturing Mars in the past.
Do we know that was a shoreline, if there was water there?
That's what the people at JPL think, and if they think so, I think so too, because they don't post anything without a large number of researchers behind it. So we're going to talk about Mars. And if we get to the end of the talk, we're going to talk about M67, which is an open star cluster, and start to think a little bit further beyond our solar system. So are there stars out there that have exoplanets that potentially have life? So yes. And a little bit about comets. Okay. So we're going to talk about bodies in our solar system which may harbor life. And we're going to look at Europa, Enceladus, and Mars. And we're going to use Earth as the example of what we consider life to be. So we're sort of looking for Earth-like life on these places. Which leads us to the next question. What is life? So some people consider life to be a chemical system that is self-sustaining and capable of performing Darwinian evolution or reproduction, but we get into a bit of a conundrum there with something like a mule, for example, which we know is alive and is life, but can't reproduce. So it's not an ideal definition. Sometimes life is also described as being founded on liquid water. a source of energy, and a group of biogenic elements. So on a moon or a planet that had these conditions, liquid water, a source of energy, and biogenic elements, water, a source of energy, and a group of biogenic elements, we would consider that grounds for going to explore further, or sending another probe, or sending another research mission. So here on Earth, life survives in extreme conditions. So we look to these what are called extremophiles, little microbes that survive in really harsh conditions, for an idea of what might be on another moon or planet. So here on Earth, we find life at temperatures from 122 degrees centigrade to as low as -15. So out in Antarctica, we find life, and at very hot places like hydrothermal vents, we find life. And then a couple of things there. UV radiation at very high levels is tolerated by various microorganisms and is therefore not thought to be a limiting factor to life. And salinity and pH as well are not likely to be the limiting factors on other bodies, because we do find microorganisms on Earth in really intense pH situations or high salinity. And so we're thinking liquid water is the key. So this is just a little table. Shows the key requirements for life: energy, light, chemical energy, carbon, liquid water, and nitrogen, phosphorus, sulfur, and sodium. And we see that liquid water is the only one that is rare in our solar system. Okay, so I'll tell you a little bit about Europa. So it's approximately the same size as our moon, and it is in a tidal resonance with Io and Ganymede, which are two other moons of Jupiter. It rotates on its pole every 3.6 days, and it also has an orbital period of 3.6 days. And the tidal resonance causes an eccentricity of orbit, leading to strong tidal flexing on Europa. So the heat and the crushing of the outer ice shell is from that tidal resonance with the other two moons. So Galileo was the spacecraft that studied Europa quite a bit, and it showed that it was internally differentiated. So inside of Europa, there is a rocky sort of core to it, and then 100 kilometers of ice, and that's either in liquid or solid form. So it's got a very thick ice shell on it. And the temperature of Europa's surfaces range from minus 190 degrees Celsius, which is very cold at the poles, to approximately 140 degrees Celsius at the equatorial region. So that's a really big range of temperatures to try to look for life in. Oxygen from the surface is responsible for its near vacuum atmosphere. Well, there's a little bit of oxygen coming off the surface of Europa. So, lots of studies have been done on the geology, theoretical studies, magnetic field measurements, and spectroscopic measurements have all pointed to the fact that there is a liquid ocean underneath that ice shell. So nobody's actually sampled it or seen it, but from all of these experiments and research, they're pretty sure that there is a liquid ocean underneath the ice shell. And Europa has a surface albedo, which just means how bright it is. of 0.7, which suggests that the surface is really youthful. So it means that not a lot of craters get to leave their mark. It's sort of resurfacing quickly. Oh, and then I put in an extra slide there. So the salts that are observed on Europa's surface are sporadic in their distribution. And they're essentially from spots that have chaotic terrain that have been disrupted. So it's sort of cracks in the ice, and the seawater is coming up to the surface and evaporating into really quite strong salt that's, it says, can reach 99% salt concentration. So we've also identified hydrogen peroxide as a component in Europa's ice spectra, as well as magnesium and sodium, and found with water molecules. And that's the same slide. Okay, here we go. So this is a comparison of Earth's seawater to what they believe European seawater is like. And so we can see that there's some similarities with the magnesium, the calcium, not too different. So this image is by Galileo. It's by their solid state imaging equipment, and it was taken in 1998. So in 1998 they were this close and taking images of the surface. So this image is approximately 220 miles wide, which is 350 kilometers wide. And essentially they're interested in areas of chaos terrain, which is sort of maybe down here where the surface has been disrupted and sort of rejoined. So it's cracked and rejoined. And they're interested in how that is going to bring nutrients down into the ocean to potentially start life in the ocean.
So that's an ice surface we're looking at?
Yes, that's ice, and this red stuff is salts. And actually I'll get onto the next one here, which is very similar. So this is the blue-white terrain indicates pure ice water. So all this sort of lighter colored stuff is pure ice water. And the reddish areas contain water, ice mixed with hydrated salts. The potentially magnesium sulfate, or sulfuric acid, and the reddish material is associated with the chaos terrain.
What are all the lines? Are they cracks in the ice?
Yeah, they're cracks. Yeah, so that tidal flexing that happens with the two other moons kind of like get it to kind of crack. Unlike Enceladus, which they believe is cryovolcanism that's happening.
Can they actually monitor changes in the surface, the visual changes of the cracks, or are they kind of frozen in time, so to speak?
Well, I mean, these are pretty close flybys that happen with the Galileo spacecraft. So they're talking about in the future, you know, look at this as a potential astrobiological target, and start to sort of design equipment and a mission to just look at life on Europa. So there's evidence of plate tectonics on Europa, and they believe this is one of the ways that nutrients are being mixed in the ocean. So they're interested in studying the plate tectonics more. So this is just part of the crust being subducted here.
And the crust is ice.
The crust is ice, yeah. So this slide is more about limiting environmental factors when compared to Earth. So time, pressure, salinity, temperature, desiccation, and radiation all work together to limit Earth's biological activity. The same things we're assuming would limit biological activity on other moons and other planets. So 250 million years, organisms lay dormant here on Earth and then come back to life when the environmental conditions suit them. So there could be life that's, say, frozen in some of the ice shells. There's potential there. And they're pointing out the Deinococcus microbes are 4,000 times more resistant to radiation than humans and can survive in these extreme conditions. So on a lot of places that don't have an atmosphere to protect any potential life from UV radiation, we're saying, well, there's organisms that do thrive and survive in high UV environments. So, potential habitats on Europa. The seafloor environment, the brine ocean, and the ice layer are all potential habitats on Europa. So they're thinking that because of the low temperature and the radiation on the surface, that there would be no life on the surface. But they are interested in sort of underneath that ice. Suitable temperatures and liquid water may be found at the base of Europa's ice layer. So we can think of Mariana's Trench as being a sort of similar environment on Earth to what they're thinking they're going to find underneath the ice layer on Europa. As well as looking at Antarctica and the Arctic for those extremophile microbes and thinking maybe there'd be something similar on Europa. So, high pressures, salinity, low temperatures, the available nutrients, energy source, and liquid water are all the things they're interested in on Europa in terms of finding life. The gravity measurements made by Galileo did reveal this liquid water with the ice shell, so that is 80 to 170 kilometers thick over top of a rocky metallic core and mantle. So it is differentiated in there.
What kind of radiation?
From the sun and also from Jupiter. So Jupiter has a lot of radiation that it gives off, and it sort of bombards the surface of Europa. Yeah. So nobody's willing to say there's definitely an ocean, but there's all this evidence pointing towards the fact that there is a liquid ocean underneath the ice shell.
I heard a talk years ago at the RASC in Vancouver. I think it was, they figured that it's moving because I remember the speaker showing cracks that were in different positions, but that matched up, that must have moved.
Oh yeah.
So that's how they, like it was moving around, and I remember the speaker matching up the cracks.
Oh, nice.
From the ice. This is quite a few years ago, maybe 15 years ago. I can't remember who or what, but they showed how the movement was because of the matching up of these chunks.
I think that they collect imagery over the time frame that they have, and then would do some sort of change detection with the imagery, I would imagine.
Yeah, I can't remember how it was, but it was something along. But it was. I remember that like an analogy like a jigsaw puzzle. They could see this piece fit into this piece, but it had shifted.
Well, definitely with the chaos terrain, it's recently been disrupted. There's no craters, it's smooth, icy surface, so it's definitely looking like it's being resurfaced on a somewhat regular basis. So, Europa Clipper, this is the mission that NASA is talking about doing to go to Europa. And they would like to look at the ocean and the ice shell to see whether or not there is life there. And they also want to look at the geology of Europa and see whether or not that would also be sort of a precursor to life.
Question.
Mm-hmm.
Would the energy source for life be sort of assumed to be kind of like a chemical underground volcanic? Or is there any hope that, say, it would be the sun?
Well, it wouldn't be the sun because the surface is too cold and too hot. And it's also being bombarded by this radiation from Jupiter. So they're sort of looking underneath the ice and saying, well, maybe, far down underneath this ice shell, there might be some suitable conditions.
But like volcanic or something?
They haven't talked about cryovolcanism on Europa, but definitely on Enceladus, there are volcanoes underneath the ocean.
The other thing was, when you were talking about the range of temperatures on the surface, I think it struck me that it said minus 140.
Yeah.
Minus 190.
So it was not
Minus 190 to
minus 190 to minus 140.
No, but I saw a minus there.
Yeah, I saw minus there too.
Uh-oh.
And it sort of seemed more consistent with the Kelvin temperature.
It's possible that there's a mistake.
Yeah, it was.
That's the one.
Oh,
That was the one.
There was that.
Next one. A minus?
Yeah, minus 140 degrees Celsius.
Yeah,
Minus 190 degrees.
So for K to 130K is still far below zero.
It's a 50-degree difference. It's nothing wrong with that.
Too hot, too cold.
Was that?
It's minus. It's only a 50-degree.
Well, it was minus 190 Celsius to minus 140 Celsius.
It's only a
There's
50.
minus up in the previous line.
It's only
Right.
a 50-degree transition.
Because, the Earth standard was, the coldest was minus 122.
Right. Right, okay, I see.
So that's
I
minus 100 and minus 50.
definitely minus 140 degrees Celsius to minus 190 degrees Celsius, I would say.
So it's still.
It's a 50.
Minus sign.
Previous slide.
Yeah,
It's a 50-degree shift,
yes,
whichever scale you use.
sorry guys. Okay, let's get back to Enceladus. Enceladus is my favorite moon, my favorite body in the solar system. It's a sweet little moon of Saturn, and it is very icy, and it has a very high surface albedo, so it just looks like this bright ice ball out there. This is a picture taken by Cassini. So, small moon of Saturn, 504 kilometers in diameter, and it orbits between Mimas and Tethys, which are two other little moons of Saturn. It's in a mean motional resonance with Dione, which excites its orbital eccentricity. It has a high geometric albedo of 1.4, and it has an association with the E-rings. So essentially the stuff that's coming out of the geysers on the South Pole, that material is added to the E-ring, and it's also sort of swept back onto Enceladus. And in the past, there's been various models trying to account for how do we get these temperatures, and really what they've come to the conclusion is that water ammonia is responsible for the mechanisms that are happening in perhaps is affecting the melting point of the water. So, the active plumes that are erupting from the south pole of Enceladus make it the only known geologically active moon in our solar system. So you can say, well, we think that Europa maybe has got some activity, but I know for sure on Enceladus they have these volcanoes underneath the ocean that are heating the water and are melting the ice. It's fracturing and it's spewing out quite a lot of water. And the southern polar activity, there's sort of 4 big cracks on the south pole where water comes out of water ice crystals.
What do you consider a higher mass hydrocarbon? Propane or octane or something?
I don't know. A higher mass hydrocarbon. Anybody? I'll have to get back to you on that.
Where's the reference?
I got the references at the end there. So on Enceladus, there's the hydrological cycle that we need, as well as geologically active and life-generating reactions that are sufficient enough to create a redox gradient favorable for life. The plumes that I was talking of, they extend 80 kilometers from the surface, and that's why you can see a big plume coming from the South Pole. They think that because of the chemicals that they have found, that it would be possible for amino acids to form at the rock-water interface. So the rock-liquid interface of Enceladus is the #1 habitat potential spot.
How far down is that? Is that right at the surface?
That's right at the surface.
So-
Or no, sorry, the rock-liquid interface is future research to figure out exactly where it is that the water starts being liquid. Yeah.
So the clay is then coming, they postulate the clay is coming from degradation of feldspars?
I think olivine. There's a slide coming up here. So there's one of the surface, a close-up of the surface. And so this picture was taken in 2015 by Cassini using a spectral filter which preferably emits UV light. And it was taken at a distance of 12,000 kilometers away. Gives you a little bit of an idea. Yeah, so 243 feet per pixel. Not sure if that's helpful, but anyway. I have another one here. This is the most extreme close-up of Enceladus that was ever taken. That actually has a scale on there. So gives you a sort of image in your mind of what the ice looks like on the surface there.
And what is the scale that it says there?
1 kilometer for, well, an inch, but
1 kilometer.
yeah, something like that. So this is what they believe is happening underneath the surface of Enceladus. We have the tiger stripes, as I mentioned, the geysers, and the ice is brittle at the surface. And so that sort of leads to cracking and the other sort of surface features that we see. And this is about trapping of methane in Enceladus oceans. So they believe the geochemical reactions are olivine and water producing methane, and it's just sort of being stored in the ocean underneath the ice there.
What's in
Olivine
olivine?
is almost like jade.
So how are you getting reactions producing hydrocarbons or carbon? Yeah. But where's the carbon come from?
I don't know. So for Enceladus, no other place in our solar system has been studied as much as Enceladus. So Enceladus, they've already decided that there's all the precursors there to life, and they would like to do another mission to Enceladus to take a look at it. And they're talking about doing a sample return mission like they did in the Stardust mission. So they have lots of ideas about this new mission to Enceladus that they're going to do. They want to create something called an ice mole that they've been experimenting with in the Arctic that's going to land on the surface and melt down to the ocean. So I don't know how practical that would be, but that's one idea. Another one is called Life, and that is to look at, well, first of all, Saturn, sample the plume of Enceladus, and then look at the atmosphere of Titan. Okay, on to the next planet in our solar system that may have at one point had life or potentially now has life. So this is a picture of some snow on Mars, on the sand dunes there. And some information that we probably know about Mars is the fourth planet from the sun, and it's known as the red planet due to the iron in its soil. More than half of Mars is covered in volcanic deposits, and there's plenty of evidence of ancient running water on the surface of Mars. There's channels, there's craters, there's fluvial sediments that they found in Yale Crater. And so they're thinking these are the type of places that they would like to look. The vertical distribution of water vapor is the key to study Mars' hydrological cycle. So they're very interested in looking to the past when there was water on the surface of Mars and saying what happened. Like, why is Mars now a hostile environment to life? And I, of course, loved it that somebody said that the subsurface water that could have existed in the past on Mars has now all turned to serpentine, which is a type of jade-like rock. And I just wanted to show you some beautiful imagery of Mars. This is, I believe, from the Mars Reconnaissance Orbiter. Yes, showing icy layers. So high levels of UV and ionizing radiation means that Mars is now anoxic, so no oxygen, and sort of hostile to life on the surface. So they're thinking, well, the places to look for life are not on the surface, underground. This is an image showing where some water may have run in the past. And there's a long list of places here that they think maybe there would be life. So lava complexes, hydrothermal environments, caverns, basins, aquifers, structurally controlled conduits, evaporate deposits, and marine and lake deposits, as well as Antarctic-like soils and vent structures, as well as icy bodies. So all the sort of more extreme places that we find life on Earth, they think, okay, maybe if we look there on Mars, we'll find something. So they think these are sedimentary layers that have been eroded. So possibly erosion by water, but more likely wind and sand. And here's some valleys that used to have water, or some channels that used to have water on Mars.
Now, did they actually know that there was water there? Or
Yeah.
did it-
Yeah, they're sure that during the Nokian time there was water on Mars, and you can actually look at some pretty amazing maps that sort of show a historic reconstruction of where the oceans used to be. So, I don't think they're planning on doing another big mission to Mars that I know of, but there are rovers and 3 orbiters that are usually going around Mars as we speak. And they are looking for the essential ingredients of life as we know it. The Mars Science Laboratory looks at soils, rocks, landscape imagery, soil textures, and determines chemistry in situ with the machine that it has on Mars, and also monitors the background radiation. So the next sort of steps in astrobiology for Mars are to detect organics of any kind and demonstrate that they are native to Mars, so not come from a meteorite, for example. And on Europa, the next steps include determining the nature and accessibility of the ocean. On Enceladus, Cassini was there for 10 years studying it, so they already know that it has a high astrobiological potential. And they're talking about doing this, a sample return of the plume. Those are the references. They're very small. If anybody's interested in them, I can definitely give them to you after the talk. And we're going to go on to something else. This is an open star cluster called M67, and it's just the idea that there could be lots of life beyond our solar system, and there's plenty of stars out there that have exoplanets orbiting around them. I think they've found at least 3 stars in this open star cluster, which is very well studied, that have potential planets that they think, oh, maybe there's life there. This is a little blurb about open star clusters that say, why are open star clusters important? Well, they're important because all the stars in an open star cluster are at pretty much the same distance and are at the same age. So that all the stars in an open cluster have developed from the same nebulous. Yeah.
How far away was that? When you were talking about?
I think it's between 800 and 900 parsec away. Yeah. So it's 4 billion years old, which is one of the oldest star clusters. Usually we associate really old star clusters with globular clusters, but this is an open cluster. And it has a lot of stars that are very similar to our sun, that have similar metallicities and similar sizes as our sun. So they actually thought for a while that this was the birthplace of our sun, but then have later disproved that. And this is the Rosetta mission. So it's a little bit about comets and do they bring life to Earth, for example? Something to think about. I'm going to give you one of my artistic images. So this is a false color ramp of the comet, and it just kind of shows the jets that are coming off of it. So a long time ago, people thought of comets as being these icy conglomerates, these sort of ice balls, dirty ice balls, I think they call them, or dirty, yeah,
Snowballs.
dirty snowballs. And that was a very popular idea that happened in the 50s with Dr., I think his name was Fred Whipple, and he came up with that theory. And since then, people who study comets have been saying, but it's not an icy snowball. It's we believe that comets were formed in the inner solar nebula because there's been a number of sample return missions where they actually captured some dust from a comet and analyzed it. And there's also been a mission called the Temple mission where they had a copper exploding kind of, not a bomb, but an impactor that smashed into a comet and broke it apart so that they could see the interior, and they found minerals such as peridots and rubies and minerals that really form in heat. So they're sort of saying enough with the dirty snowball hypothesis. And that is the end of my talk. Thank you for listening.
Thank you.
Should we do the meteorite giveaway?
Why not?
Okay, so underneath your chair, check and see if there's a little piece of paper that's taped underneath. And please do check in the chair beside you if it's empty. You got it!
You got it.
Okay, you win the meteorite. You're welcome.
I suppose you got this chair. So thank you very much for thinking of that, Sarah.
Yes.
So before I ask for any questions, we were talking when we came into the room because it's been Pride Week, and Sarah made the comment that when you stand up in front of an audience, if you're at all nervous, it's good to imagine your audience naked. Easier today than perhaps. Anyway, any other questions for Sarah?
Yeah, I've been interested in the different chemical pathways from non-life to life. Like, there was an article in Scientific American about the RNA world, which hypothesized that replicating RNA, self-replicating RNA molecules were the beginning. And then there's another hypothesis that says that it began with the membrane, where membranes, as in the bilipid layer of a cell membrane, that type of membrane was first formed on a clay substrate, and then those membranes became like bubbles which could enclose a variety of different chemical conditions, which then became life. Mm-hmm. I don't know if you, are there more of those hypotheses?
Well, I think on Mars they're suggesting a life that's based on chemilithoautotrophy.
Mm-hmm. Mm-hmm.
So that's like chemicals, rocks, doing it themselves, life.
Mm-hmm. We have slimes on Earth.
Yeah.
Down there.
Yeah. I'm not sure if that answers your question. Not really.
Not exactly. No, it's the pathway from just non-biology to biology. So, you know, like the self-replicating RNA idea is a very good one because RNA is in between protein and DNA, right? It's like the mediator in between the two. So you can see how maybe RNA formed first, you know, given all the combinations and permutations in the
We had a talk earlier this year
Uh-huh.
from a professor from the Hong Kong University, and he was also talking about astrobiology. And one of the things he was doing was looking at supernova and the data we get back from the light from a supernova when we have a chance to capture it, and what occurs in the first few seconds and so on. And he was looking at that to look for the molecules that would be necessary to make RNA. And virtually everything that you needed is there.
Oh, yeah.
So it's out there, and therefore conceivably could have made its way onto the clay
Certainly.
and started the process.
How did they think water got on those moons? Same as the Earth, through meteors or I mean comets?
I didn't come across that when I was doing this paper. Yeah, a lot of times they think that it's like meteorites bombarding that would lead to water. But I don't know exactly what their theory is. I mean, to me, it's like you look out there and there's these two moons that are full of water. So some similar process has happened there, like compared to Earth, I would say.
And did you say that they detected oxygen in Europa's atmosphere?
There's oxygen bound somehow on the surface of Europa, and it is sort of going very minute amounts, trace amounts, I think, into the atmosphere of Europa, but there's a vacuum for an atmosphere on Europa, so not much of a atmosphere. Yes?
Have there been any theories that life at one time existed on Mars, but due to a cataclysmic event has disappeared?
Well, something definitely happened, and they're researching, what happened from the Noachian period to now to make it so that it used to be this habitable world that was full of water and oceans and rivers and lakes, but.
So are analogies being drawn to potential cataclysmic events that could be human caused on Earth?
I've never heard of anything like that humans caused the sort of potential mass extinction on Mars, but it could have been an asteroid hit or something like that would radically change the environment.
But there are plenty of theories on Earth about the Silurian hypothesis and so on, and there were earlier civilizations, and the Anthropocene is just going to be the next Silurian extinction. So,
Yes.
but is that science? I don't think so.
What's the significance of the announcement they made yesterday, NASA made about what they found with the rover on Mars?
I didn't hear the announcement.
Well, they said they found some, it was on at 2 o'clock in the afternoon.
They found methane, and the source of the methane, they think, with further analysis, that they'll be able to determine whether it came from a geologic or a biologic source. Because methane could be formed by an organism, or it could be formed by geologic processes. And they're hoping to be able to determine that. So.
Yeah, there's a little clip on, you can find it on Google.
Okay, I'll look it up.
I think the interesting feature about the methane is they've been detecting it for, I think it's 1.5 years or 2 years, Mars years, and it varies through the seasons, and which is a real puzzle, because if that kind of lines up with a life origin. If you imagine that the methane goes up in the summer because there's more warmth and potentially more life activity. But there's other bits of the puzzle that just don't fit, because methane is very long lived in the Mars atmosphere. Like it's not being removed. So why is it going up and down if it's not being removed? So the picture just isn't kind of coming together. But
what's the freezing point of methane?
I can't tell you.
That's very important.
Well, it's not too low, because we have frozen methane on Earth in permafrost.
Yeah.
Well, just
When you were making reference to your artwork,
Oh, yeah.
you mentioned that you used algorithms to
Mm-hmm.
determine
So they're
colors?
just filters, so it's a little bit like fancy Photoshop. So I'll take an image, I'll look at the histogram, so look at the digital number values, and I'll try to think, is there any more information in this image? And a lot of times I'll just try different algorithms, an edge detection, a classification algorithm, and see if that draws out any more details in the imagery. So sometimes I'll get an image that has got a black sky, and then when I do processing on it, it actually has a whole bunch of little particles of Saturn's rings that you can't see in the dark. But if you do a reverse image, you can see them. So a lot of times I just play around with the images.
And so it's really mathematically composed.
They're Boolean operators. So they're just sort of going along in a little matrix over the image and changing pixel values to get whatever the desired outcome that you want. Yeah. Usually edge detection.
The freezing point of methane is minus 162 C. The methane that you see in the permafrost is hydrate, so it's trapped methane within inside of a 14-sided cage.
Okay, thank you.
I'm just curious, you were talking about the possibility of using a mold to get down and melt the ice. Like, what about contamination? Is there not a possibility of contamination? That might be a bad thing.
Yep, absolutely. So that's something that they consider when they're designing their experiments to make sure that it's in a clean room. But I've seen pictures of clean rooms where they build this equipment that have microbes in them.
Right.
So, yes, they have to be very aware of not bringing their contaminated bias in there.
Okay, well, thank you very much, Sarah. That's been a very interesting.